Hey everyone, welcome back to the xHCI driver development series. In the last part, we've started the controller and put it into the running state. So now it's time to tie everything we've done together and send the controller some commands and get the responses back in the event ring. This tutorial should be a fun one, so without further ado, let's jump right into it. At this point, you're probably familiar with this diagram from previous tutorials where the OS places a request into the command ring and the controller will look at it and generate a response, at least according to our understanding so far. However, in reality, when you place a command onto the command ring, nothing happens, at least immediately. The controller doesn't sit there waiting for your commands and waste resources. There is a specific mechanism, though, that we can use to notify the controller that there is a command pending, and that is through what's called doorbell registers. These doorbells are 32-bit registers inside the xHCI memory space, and just like how you'd ring an actual real-life doorbell to get the attention of the person inside the house, you'd have to ring these doorbell registers to get the controller's attention. And depending on which doorbell you ring, the controller will look at different rings. As of right now, we only have the command ring and haven't covered endpoint transfer rings yet. So we will only have to care about the first doorbell 0, which corresponds to the controller's command ring. So by ringing it, we'll notify the controller of the pending request, get it to process the command, and generate a command completion event in response. The actual process of ringing one of these doorbells involves simply writing a target value into the 4-byte doorbell register, and the official spec clearly outlines how to calculate and come up with the right target value. We'll definitely cover the target values in more detail later, but for now just know that the doorbell 0 requires a target value of 0 and corresponds to the command ring. I love how ringing the doorbell is an actual technical term here. Well, let's see it in practice and get to coding. Let's begin by opening up the xHCI regs.h file and adding the struct definition for the xHCI doorbell register. Each doorbell register is very small and simply consists of a 32-bit unsigned integer, but for our convenience, let's also break it down into individual bit fields as well. Now I also want to define a doorbell manager class to make life easier in the future, and its purpose will simply be to store and give us a nice and easy to use access to different doorbells. As the only private member variable, it will store the doorbell register array. The constructor will also be very simple and just take in the base address of the doorbell registers. Now let's define a few public functions. The first one is going to be the most general one, and it will allow us to ring any doorbell with a provided target value. The target value can be found using the following formula: 2 plus the 0-based endpoint index multiplied by 2, plus 0 if the endpoint is an out endpoint, otherwise 1. Don't worry about this too much right now, I'm just writing this ahead of time now to make things easier to remember in the later episodes when we do cover the device and endpoint setups. And finally, we'll define two more functions, one to ring the main command doorbell, and another to ring a control endpoint doorbell for a given device slot. Great! Let's now create the xHCI regs.cpp file, since we don't have it yet, and start implementing the class there. The constructor will be super simple, and we'll just cast the 64-bit integer base to the doorbell register array. Next up, the general ring doorbell function will take the specified doorbell register and write the target value into it using a 32-bit dword write. Great! And then the final two functions will reuse this ring doorbell function and call it with constant values. For the command doorbell, you have to ring doorbell 0 with a target value of 0. And for the control endpoint, you specify which device's doorbell you'd like to ring and write a target value of 1 into it. Great, our doorbell manager class is now done. Let's now integrate it into our xHCI driver class. Below where we define the event ring instance, let's define an instance for the doorbell manager. Let's now go into our parse capability registers function, and below where we define the runtime registers, we'll instantiate our doorbell manager. As for the base parameter, we'll pass in the host controller base plus the doorbell offset field from the capability registers. Awesome! Let's now go up to our start device function and test out sending a command. Let's also get rid of these old USB status prints. Cool, so the first thing we're going to do is create an empty TRB struct and zero out its memory, and set the TRB type to the value of 9, which is the enable slot command. which is a good and fairly common command to be testing your driver with. Next, we'll enqueue the TRB onto the command ring. And finally, we'll use our newly created doorbell manager to ring the command doorbell. Alright, so now let's compile the project and see what happens. And we get a kernel panic, a page fault to be exact. This is actually expected right now because when we rang the command doorbell and the xHCI controller processed our command and generated a completion event, it raised an interrupt to notify our OS of it. My kernel's PCI device driver parent class reserved an interrupt vector to be used for MSI or MSIX interrupts for the xHCI controller. But no handler was ever installed, so when our IRQ was fired, the control went to a dead region of memory and caused the page fault. So now let's go into the code and implement and install the interrupt handler for our driver. The way you install interrupt handlers in your kernel may be different, but in mine the signature requires a ptregs pointer, which can just be a void pointer here since we don't care about them, and a user data pointer, which in our case would be useful to pass our driver's instance to the handler. Let's now go into the CPP file and implement it. Right before returning, my kernel requires you to call this IRQ send end of interrupt function, so we'll do that here. Additionally, right before that, we have to call our driver's acknowledge IRQ function that we defined earlier in the series when talking about the runtime registers and interrupters. Alright, now we can actually focus on the rest of the handler. And all we're going to do for now is dequeue all of the newest events off of the event ring and just print them out and log their status fields. This is also a great way to test our implementation of the event ring and make sure it works. Now that we have a valid interrupt handler implemented, we have to actually install it to be used. Again, you will most likely have, or at least should, have your own function to do this for your kernel, whether it's through abstractions or just modifying the IDT directly in x86, but the goal here is to direct the control flow to our driver code on an interrupt raised by the xHCI controller. Great, so now when we ring the command doorbell, our interrupt handler function should get called properly. Let's compile and see. Amazing. As you can see, our interrupt handler was executed correctly, and our event here has a status indicating successful command completion. Let's also open up and look at the QEMU generated xHCI trace logs and see what they show. There's our run message for when the controller was started, and then we have the xHCI fetch TRB event, and it correctly fetched the enable slot command. Then we see the actual slot enable trace, which actually enabled the device slot in response to our command. And finally, we have the xHCI queue event log, placing the command completion TRB onto our event ring. This is great. We now have a functioning workflow of communicating with the controller. But let's take it a step further and do some engineering to make it actually scalable and reusable. First of all, let's go into our xHCI TRB.h file, and so far we only have a generic TRB structure. But we'll now define a more specific struct for the command completion event TRB. The first field will be a 64-bit pointer to the command TRB that caused this event. Then we have 24 bits that are reserved, followed by a completion code, which is 8 bits. And the last 32 bits include our usual cycle bit, TRB type, and finally the slot ID for the executed command. Cool. So now looking at our interrupt handler, the code that looks through the event ring is the first obvious one we can abstract away into its own function, which we can call process events. Now, I also want to declare a vector for specifically command completion events, and you'll see how this is going to be used in a second. And we'll also need to declare a flag variable that will tell us when a command completion event is available. Alright, cool. So the first thing we'll do in our process events function is pretty much what we did in the IRQ handler above, so pull the event ring for any completed events. Then we'll need a local flag indicating whether this cycle of processing events had any command completion events. Because remember, the event ring won't have just the command completion events, but also transfer completion events, port events, and other sorts of events. So we need to know if any command completions occurred. So then we'll iterate over every dequeued event and check if it's a command completion event. In which case, we'll set the local flag to 1 and add the event to our vector we just created. And finally, we'll set our member flag variable to the value of the local flag to see if any command completion events are available. Now we can go to our interrupt handler and replace the first half with our new process events function. Awesome. Now that we've abstracted away event processing, let's also look at the way we send commands and see if we can abstract it into its own function, as well as look for the corresponding completion event all in one. So let's go into our class header and define it. It'll take in a pointer to our command TRB, and take in an optional timeout in milliseconds so it doesn't get blocked in case the command gets dropped by the controller. First thing we'll do here is enqueue the TRB onto the command ring, and just like we did before, bring the command doorbell. Then we'll have to wait for the interrupt handler to get called, and the process events function to add any command completion events to our vector. And we can do that by spin loop waiting on our flag variable we declared and set to 1 in the process events function after all the processing is done. Also, there is an important assumption to this entire event processing design. It assumes that you will be sending only one command at a time, and will not send another one until after you've received a completion event back. Just keep that in mind. This way we can simply check if the size of the command completion events is not 0, and if so, the first one is the one we need. Otherwise, we'll just set the completion TRB variable to a null pointer and consider the command failed. Cool! Now that we've grabbed the corresponding completion TRB, we need to clear the command completion event vector and reset the IRQ completed flag. Finally, we can put in a couple of checks to validate the completion TRB and print out the appropriate error message if something went wrong. Now, if the completion TRB was found, but its completion code was not success, we should print out what went wrong and display a nice message with the actual completion code. And for that, I'm going to copy paste a couple functions here into the xHCI trb.h that will make life easier. I'll also leave a link to this file specifically in the description so you can easily copy paste it into your project as well. And finally, if all checks passed, we simply return the completion TRB. Let's now go back up to where we sent our enable slot command and replace it with our newly created function, and you'll see just how much easier our life has become. And if the completion TRB was valid, let's print out the completion code, and most importantly the slot ID. For any other command, the slot ID would be the device slot the command was destined for, but for the enable slot command specifically, it's going to be the ID of the first available slot that was just enabled. Let's now compile the project and see if it works. And would you look at that? Our completion code is 1, meaning success, and we just enabled slot 1, which matches what we saw earlier in the trace logs. For demonstration's sake, let's go back into the code and try to send multiple enable slot commands. So we'll call our send command function repeatedly in a loop, let's say 6 times. And voila! We can see that device slots 1 through 6 have been enabled, and the completion code is 1 for all of them, meaning success for all the commands that we sent. We now have a stable way to communicate with the controller, and send it various commands and receive responses in return, which will be super useful in a couple of videos when we start setting up real devices, and conveniently enough, enable slot command is the first real command we'll actually use later. Until we can start setting up devices though, we have to cover one more aspect. and that is port management. We have to be able to detect device connections, identify port characteristics, and be able to reset ports before we can actually set up devices connected to them, which we all should be able to cover in the next video or two. But for now, have a wonderful day, and until next time.